welcome back to my YouTube channel. My name is Batwiki. It's your boy. Glad to be back. It's been a very stressful time. It's been a very crazy time. I haven't uploaded a video in ages, but I think this one is gonna be one for the books because I've prepared so much. I actually have a diagram to be like, yo, this is what's happening. I don't even know if you can see that. I'll try and like zoom in on my end just so you could like peep the game. You feel me? So yeah, this is just like a calendar. But the topic that we're covering today is known as graph theory in data structures and algorithms. So what graph theory is, right? It's practically a non-linear data structure where we are able to store data in a non-linear way, which is very self-explanatory, right? Because it's like in a computer we don't, well, there's times when we usually want to store data like sequentially or one after the other. A good example of this would be like when you're using your file explorer. It's like every single path that you open will lead back to the previous path. So that would be an example of a stacks, or that's one of the data structures that we've covered, which is like your last in first out. So as you keep on going, the last input that you placed in will be the first one to go out in a sense. But yeah, let's just continue working with this. So to introduce you to graph theory, I think this I'm gonna make this into a multi-part video because I don't want to be yapping for a good hour. I have a lot of notes on this, but in essence, I think there's a couple of things that you need to keep in mind. So it's just going to be the introduction to the topic, and from the introduction, we're then going to venture into the different components because I think it's very easy to piece together that information by basing it on the components of a graph rather than like looking at a graph and trying to dissect like the small details of it. So, not the small details of it, more so like just understanding, okay, this is a graph and this is what it does. That's pretty much what I'm trying to do for this video. And then for the next video, we'll have to cover the traversals from this video. And then from the traversals video, we'll go into code implementation and so on. So I'm just going to start here saying that we have to start with the Königsberg graph theory, right? So the Königsberg graph theory was introduced by Leonard Euler in the year 18 something. But yeah, here I just have in the diagram, I'm practically saying, okay, the Königsberg bridge problem was discovered by Leonard Euler, and the main theory behind graph theory is being able to traverse, so being able to travel across. That's why we call it graph theory with Königsberg bridge problem, because you travel across bridges, right? And then I just jump into here saying graph theory itself was discovered by the mathematician, and we can see that we're able to chart a graph, which would be this component, based according to the nodes and edges that we set to a problem, which will help identify the problem to solve various traversal problems. I hope that made a lot of sense. It's a lot of redundant wording in this, but it comes along. So the vertices and edges in this case would then be the land and the bridges that are connecting the various pieces of land. And and in this case, a question is asked by Euler, and that is, would it be possible to visit each piece of land without ever having to use the same path again? And those are the fundamental concepts behind graph theory, is that we want to find solutions to how we would go about traveling through certain, not just static instances like going from point A to point B, but also figuring out, okay, in a network, which is the shortest path in a network, not physical terrain. So I just drew a diagram here stating that the bridge itself, which I'll go back to in my notes, so like you can see in the notes, it's just the same bridge here. So the bridge itself, right, we are then able to diagrammatically represent that as a set of vertices and edges. So what the vertices are, right? As much as he calls them nodes here, we call them vertices in a graph, because with the vertex, right, we have the paths that connect two vertices, which would then be the edge between the two vertices. So with this, calculation that's here, we can take note of, okay, this is how we would say graph is then a collection of vertices and edges. And then we have to note that graphs are actually data structures which store information, and we can then assign values to various edges and vertices and then perform algorithms. And the algorithms that we primarily perform are traversal algorithms, or finding a path between point A and point B. So after covering that introduction, here's one that furthers what we've been saying. So here I just state this is a simple graph, a non-simple graph with multiple edges, non-simple graph with loops. So as we can note that a simple graph doesn't contain any loops, and it yeah, it doesn't matter also if like the points intersect and stuff like that. So that's pretty cool. Then I'm like, the graphs above are what we would then visualize the application of the problem, such as Königsberg graph problem, because we only want to visualize the way we implement this in code. It's like you can see how it's happening in the code, but it doesn't look as graphical as what is happening on the screen right now. So as we continue with that, I'm just gonna zoom out on myself a little bit. So, graphs are considered to be a set of objects that have vertices and edges. So, to denote this relationship between the elements, we would say G is equal to V and E, right? And within V itself are a collection of values, and between E itself are a collection of values. So, these are the set of objects. So, that means we have a collection of these edges and vertices, such as the images above, where we denote the vertices as dots, the pieces of land, and the edges, the bridges connecting those, because even with the edges, like, we end up referring to them as the paths. So anytime you think of a path, you're thinking of a way to go, right? Like there's a certain path that you need to take. So I think after covering that is where I'm going to jump into the components and the concepts of graphs, and then I'm going to cut the video here as the first part. So, understanding the components and concepts of graphs, right? We have already denoted like a simple graph is a graph that doesn't contain soft loops and parallel edges, which are just various edges that share one common vertex. The vertices, bear with me. So that's simple graphs. Disconnected graphs, I didn't define it here, but disconnected graphs are practically graphs that will have a vertex that is not connected to the rest of the graph. So it's disconnected. So when analyzing the graph above, right, vertex 5, which is right here, isn't really connected back to the entire graph, and that's how we would go about identifying disconnected graphs, as there's no path that connects all the vertices of the graph. Okay, I was mistaken. So disconnected graph just means that the whole entire thing doesn't come back into one initial route. Like you can't travel around the whole entire graph. There will be like one path missing to connect the entirety of it. And then I'm like, we jump into defining a path. A path is simply defined as the edges that connect the vertices within a graph. So in that case, when we look at the diagram above, we can take note that E6 falls in between V3 and V4. So that is the path from point A to point B. It's just like the walkway, practically. And then disconnected graphs are what I was saying. So I was just saying that when we have a vertex that is standing alone and is not connected to the rest of the graph, that would be a disconnected graph, because there's no path that connects the entirety of the graph back to like point, like you can't traverse all the points and go back to point A, because it's like it's disconnected. You can't like teleport from the island into the graph that has the roads in a sense, but that's just a silly way of putting it. And then directed graphs are when we have directional arrows that flow from each of the respective indices, or not indices, I should have said vertices, that are within a graph. Sure thing. And then defining the degree of a vertex. And then this one is just, I think, not more advanced, it's just a little bit more critical in understanding how to define the degree. So this concept covers the fact that we define a degree as the number of edges that are in incident with the vertex. So once again, I shall use the diagram above to display how degrees are formed in a graph, right? So with V4 right here, we can see that it's connected to V2, V3, and V5, but we're not focused on the we'll get to the part, but like it's called adjacency because it's like the path that connects two vertices are known to be adjacent to each other. But we are currently focusing on V4 and all the edges that are on incident with V4. So all the edges that are currently touching. Pause. Gotta pause that statement. It's a crazy statement. I won't even lie. But yeah, you just gotta calculate how many edges are in contact with the vertex itself. So I shall use the diagram and then I selected V4 and then we can see edges E6, E4 and E7 are said to be in incidence with V4. So the function that would denote this would be degree of V4 is equal to 3. And then weighted graphs is about understanding that since we have components of a graph, the edges and the vertices, right? We can then apply values to the different components, whether it be the vertices, whether it be the edges. We can say that each vertex has a value of 10. So now we can calculate the path that will span and we'll try and figure out how many values of 10 we can calculate across traversing the entire graph, something like that. So yeah, weighted graphs are just graphs that have values assigned to each of the edges and vertices that are on incident with a pair of vertices, and this allows us to expand the functionalities as a whole since we're able to perform calculations based on the traversals. And then subgraphs and supergraphs, right? The concept of subgraphs and supergraphs is fairly simple to understand because it's like we're taking a piece of a graph and then just charting it as its own segment. So here I'm like, the concept of subgraphs and supergraphs is one that is fairly easy to understand as we are focused on charting a segment of a graph and then we can define its initial graph, which would be this bigger one, as our supergraph called G. And then with its subgraph, we would call that G1. And if our subgraph were then to contain all the vertices of our supergraph without all the edges, we would note this as a spanning subgraph, like it's spanning across the entirety of the graph but without all the edges. And then that brings us into our final point, which is pretty crazy considering it took our lecturer like 3 days, not 3 days, but like three separate lectures to get through this. And I'm like, okay, cool, I'm kind of getting it. But yeah, now we have to focus on the concept of adjacency because it is one that encapsulates the functionalities that we can perform with a graph because the way we display a graph visually and in code, right? Like a graph we can denote it as like this diagram over here, but in the process of like using code we would then get this kind of not layout, but like this is the way we should think about it when we were running the code for the graph. So the concept of adjacency is one that encapsulates all the functionalities that we can perform, as adjacency leads to us then being able to perform visualizations of the graph known as adjacency matrices or adjacency matrix and the adjacency list. And what those are, adjacency matrix is this box that I just showed you, like this table of 5 by 5. So a matrix would then have two dimensions, which would be the x-axis and the y-axis, right? And then we plot different sections of that graph according to where the edges intersect with the vertices themselves. So yeah, it's quite a lot. It's quite a spoonful. So I jump in and say we define adjacency as when two vertices share a common edge. Then the edge itself is said to be an incident between those two vertices. And this means that we have to take into account that for each edge that is on incident with a pair of vertices, then there is a path between those two vertices, or like there's a way connecting these two. And I just said that it is equivalent of one traversal from one place to another place is one traversal. And then the difference between the incidence matrix and the adjacency matrix. So we've come this far, shout out. But this is where we wrap it up because when we jump into the code, it's like that's the body of the whole thing. So I just hope I get this right. I hope you guys enjoy the video. I mean, like, comments, and subscribe. This is as natural as it's gonna get for me. Most of this is unscripted but very studied. So hey, bear with me on that. And then I'm just like the difference between incidence and adjacency. So incidence matrix, we can note that the term incidence goes back to when we defined the edge, and we said that the term incident refers to when we have an edge that falls in between a set of vertices, while adjacency, this refers to the term adjacent, where a pair of vertices that share a common edge. So I just used this, right, as our example graph this whole time. So I'm like, for the graph above, we can denote, I can just say denote, maybe denote. Uh, Let me just plug that in. Bro, my spelling is horrible. Anyway, so I did that, and then I'm like, for the graph above, denote the incidence matrix would look as follows. So, back to adjacency, right? It's like the edge that connects two vertices, right? So here I'm like E1. Where is E1? E1 is over here, and it's a soft loop, right? So is E1 on incident with V1? Nope. With V2, yes. So we plot 1 as the thingy to say that it is not as the thingy, but like as the variable. Thingy sounds unprofessional, and we've been talking about it just. Oh, that was such a dry joke. I'm sorry. I'm sorry. But anyway, we move on to V3, where we like V3 is over here. Is it in incidence with E1? No, that's over here. And then, wait, no, I'm tweaking. So let's go back to V3 E1. No, it's not. V3 with E2. No, that's not possible. V3 with E3. No, that's not possible. And then V3 with E4, and there we go. So that covers pretty much what we needed to know for now. Cause I don't want this to be a little thick. But anyway, that's me. I started. It's crazy. That's me, man, doing this programming thing, taking it serious, kinda. I've been going through a lot, but as a man, can I really say much? No. Uh, the next part will jump into how we construct the graph as code, because we've been speaking about the term adjacency this, adjacency that, right? But what it means is like we just have a two-dimensional graph or two-dimensional array that will then take in the set of vertices. So here we'll have V and V. Like if you go into the code itself, I'll just jump into this quickly, might as well. But it's like when we jump into it, I'm like, I want to add an edge, right? We just declare integer I and integer j as the stand-ins for this. Because anytime we have, me personally, throughout the journey of data structures and algorithms, is like anytime we have variables that are just like stand-ins, not stand-ins, but like those are primarily used for like keeping position of something most of the time. So I'm like, that's that free game. Like, hey, you'll note that one day, be like, damn, he was right. But anyway, um, this is just displaying the matrix, and like the code. How I can put it into words is like, for all the rows in the matrix, right? And for each value in one row, print that value. And then we just keep on doing it and doing it and doing it. And then that's pretty much it. Yeah. And then adjacency list. So I'll get into the differences of the adjacency matrix and adjacency list in the next video. But this is my time. Don't forget to like, comment, and subscribe. That word is being killing me. It's your boy Rory, aka Badwiki, signing out. It's crazy season, bro. It's exam season, so I'm like, this is the only way I can study and get this into my brain is by helping you guys. So you guys can help me too by showing support, man. All love, all love. Goodbye.